Uh, Welcome to lecture 15 of the course. We have kind of crossed the halfway mark in this course, and I think we are kind of doing good in terms of covering what I had planned to cover. Okay, so today's lecture is about correlation inequalities. We may have 2 or 3 lectures on this topic. So first, let me say something brief about what this topic is, and then I'll talk in detail about the topic once more after we see a couple of examples. Okay, so in brief, this is a technique to show that two events are positively dependent or negatively dependent. Remember that we saw these definitions of positively dependent and negatively dependent in the quiz that we did, right? So we say that A and B, two events are positively dependent if the intersection happens to be, okay, in the exam we define something known as a strict positive dependence, but more commonly the definition uses a greater than or equal to. In the quiz we had given a strictly greater than, but that was just for the benefit of that quiz. Okay, so this is when we say that two events are positively dependent. And similarly, if this was less than or equal to, this would be a negatively dependent. Remember, if it was an equal to, then it is an independence. Okay, and how do we actually most of the time show that two events are independent? Technically speaking, we should show that this P of A intersection B, we should calculate P of A separately, P of B separately, and show that this relation with an equality, not the greater than or equal to, equality is satisfied. That is how mutual independence can be established. That same trick will also apply for establishing positive dependence or negative dependence, right? But in practice, in most of the situations, we do not establish independence by using this formula, right? What we very often do is we decompose the random experiment into a collection of independent, smaller experiments. Like, for example, if you wanted to give a vertex coloring to a graph on n vertices, let's say, then we decomposed it into n independent coloring experiments, one for each vertex. And then under such a model, if let us say one event A dependent on only a particular set of vertices and their colors, and another event B depended on a disjoint, okay, that's a word there, a disjoint set of random variables or decomposed smaller experiments, then since because of the independence of these atomic experiments, we could conclude that the events A and B were independent. In fact, this we have used very much in the Lowash local lemma section to show this mutual independence. This you should actually listen to it very carefully, because again, as I keep saying, one of the very common mistakes that we hear in selection interviews is when we ask people about their intuition on what independence means, many of them confuse it with disjointness of events. Okay, so here this picture is in that sense wrong. Here what I am drawing is not the events A and B. Actually, A is some function of these events and B is some function of these other events, right? If you draw A and B in the Venn diagram of all outcomes, they will be something more like, something where it is kind of an orthogonality there. This would be A and this would be B, so that your A intersection B would be equal to PA times PB. Okay, so this is in that sense a misleading picture if you consider this as the events. But yeah, the idea is that many of the time we argue about mutual independence by saying that one event depends on one set of smaller experiments and the second event depends on a second set of smaller experiments, and these sets of experiments are independent. Okay, and hence we conclude the mutual independence. So can we, by the way, that's not a very a general way of concluding mutual independence. There are certain cases where the experiments look very much tangled, but still you have independence. One classic example is picking one number from 1, 2, 3, 4 uniformly at random. Okay, so there is no independence. It's a single experiment. You pick any of these numbers with probability 1 by 4. That's why we call it uniform. And then now consider two events. A is, let's say, 1 comma 2 and B is let's say 1 comma 3. Okay. Now these events, if you calculate all these three quantities, P of A intersection B, because the intersection only contains 1, that is 1/4. P of A and P of B are half each. So half times half is equal to 1/4. Okay. So these two events are, in fact, these A and this B are mutually independent. Knowing that A has happened does not give us any further information about whether B will happen or not, or whether B has happened or not. In these cases, this decomposition into smaller random experiments does not seem to work, at least obviously. Okay, maybe there is a very clever way of reformulating this, picking one element uniformly at random as two independent choices and on, but at least on the face of it, this is not looking like the experiment doesn't seem to be decomposed and so on. So even in this case, we have independence. Okay, so yeah, this is only a trick that works in a lot of times if you can decouple the experiment into smaller pieces. On a similar vein, to check whether two events are positively dependent or negatively dependent also, the most convincing way or the most comprehensive way would be to check this relationship if you can do that. But are there certain cases which are similar, like what we discussed just now about separation of experiments? It's not, the answer is not going to be about separation of experiments, obviously, because if it's separation of experiments, we'll only get independence, right? But are there some sufficient conditions which guarantee positive dependence, and are there some sufficient conditions which guarantee negative dependence? Okay, so that's the objective, or that's the theme of this section about correlation inequalities. Okay, but before even starting on to probabilities, we will first see a combinatorial result and then reinterpret that combinatorial result in terms of probabilities of events. Okay, so it may look like a digression when we start off, but it is going to lead to sufficient condition for two events to be positively dependent and negatively dependent and so on. We will start with two definitions about a collection of sets. Okay, so in this problem that we are going to, or the first result that we are going to see, the most confusing, or the place where you are very likely to get confused is because we are talking about collections of subsets. So at every step, you should check for yourself whether you have understood the object correctly. Are we talking about a single set, or are we talking about a collection of sets? We will use them, we will mix them, right? I mean, the argument will be sometimes about single sets and sometimes it will be about collection of sets. So pay attention to that distinction. In the scribble notes, I have tried to do some kind of a, a calligraphy kind of font or a scripty kind of font to denote collection of sets, whereas more the classical capital letters, without any wiggles and so on, or as much wiggles as I could reduce, will be used to denote single sets. Okay, so this first definition that we will see is about a down set. What is a down set? A collection of sets is called a down set. Okay, so point number one, a down set is a collection of sets. Okay, although we will just call it a down set rather than a collection or a down collection. Why? Because collection is also a set, but when I say set of sets, sometimes it may be difficult for me to distinguish. Okay, so though the word is down set, this refers to a property of a collection of sets. Okay, so a down set is a family of sets. That's the first thing that you should be clear. So a down set is a family or a collection of sets with what property? Like if any set S, okay, now this is a single set S, is in the collection, then all its subsets are also in the collection. Okay, so that by the down you mean something like that, right? If a set is in the collection, then everything that is below that set, by which we refer to all the subsets of that set, are also in the collection. This is what is a down set. Succinctly, we can write it in using this logical expression, S element of C. So here, because S is a single set, it's an element of C, and you take S prime, which is a subset of C, then this S prime should also be an element of C. Okay, that's what is a down set. Maybe I should have called it a down family, but it already has many names in literature. These down sets are also called as a collection of sets which is downward closed, which is monotone down, which is monotonically decreasing, etc. Being the shorter of all these names, we will use the word down set. But okay, now while recording, I think I should have probably skipped the convention and called it a downward closed family. But it's a very long term. But remember that this is about a family of sets. Otherwise, you are going to get confused or you are going to get completely lost if you think down set is a ordinary set of it's okay. It is a set in the sense that set of sets is a set. But it's important to note that this definition makes sense only if you are talking about a family of sets. Now, similarly, or there is a definition called upset. Okay. Now, yeah, it's almost a very, very bad choice of name. If you read it together, it will be upset. And in many times in this recording, that's how I'm going to pronounce it also. Okay. But what is an upset? Here, if this is also talking about a family of sets, a collection of sets. And here, the property that you want is that if a particular set S is in the collection, then all the supersets of S are also in the collection. But now, unlike the subsets, defining supersets you can do, or all supersets you can do only if you restrict to a universal set, right? Otherwise, it's kind of a uncontrolled being, right? Without a universal set, what are going to be the supersets? So, in order to define an upset, unlike in the down set, you need the notion of a universal set. Okay, so this comes extra in the definition of upset. Otherwise, it's a definition which is exactly similar to a down set, except that what we want is given a set is in the collection, all its supersets are in the collection. Okay, and how do we succinctly represent it? If S is in C and this S prime is a superset of S, but still a subset of the universal set. We are restricted to the power set of U. Then what should follow? Then S prime should also be in the collection. Okay. So let's see. By the way, these definitions, if you haven't heard before, it may look a bit very strange kind of objects, but these are very, very natural. So I tried to convince that by giving a few examples of downsets, subsets, and so on. So think about all subsets of, let's say, the first 10 natural numbers. By the way, this can be any, I can replace this set 10 with any set here. You take all subsets of any given set, power set of any set, you can see that it is, it's a down set or it is downward closed, right? Because for every set, all its subsets are also, every set which is in the collection, all its subsets are also there. Easy to verify. Then think about all subsets of 1 to 10 which do not contain 5. Okay. Again, pause and think and convince yourself that this is also a down set, because if S does not contain 5, no subset of S contains 5, hence that's also in the collection. But there are more interesting and more familiar properties. Okay, all planar graphs on 10 vertices, even this 10 vertices is not important here. Why? So first of all, how do we think about planar graphs or a single planar graph as a set and planar graphs as a collection of sets? A planar graph, or any graph for that matter, can be just identified as its set of edges. Okay, so now a collection of graphs becomes a collection of sets. Okay, in fact, all you need for at least in cases when you don't treat isolated vertices, a graph is completely specified if you specify its edge set. Okay. Okay. Now think about all planar graphs on 10 vertices, right? So if the set is empty, then that will be the empty graph. It's a planar graph, right? If the set has all n choose 2 elements, all the 10 choose 2 elements, then this is the complete graph on 10 vertices. It will not be planar, so on. So what is this collection that now we are talking about? The collection that we are talking about is among all these possible graphs, which would be 2 to the power 10 choose too many. Okay, it is, again, think about that. It is 2 to the power 10 choose 2 is a number of different graphs that you can have on 10 vertices. Among them, you collect all those which are planar. But now you see that this is a down closed or this is a down set. Why? Because from a planar graph, right? Suppose S is a planar graph, okay, in this notation. Suppose S is a planar graph, then what is a subset of S denote? It denotes a subgraph of that planar graph, because you get a subset, which means all the edges in S prime are also present in S, or S prime is obtained from S by maybe removing 0 or more edges. So S prime is a subset of S, and planarity is a property that is preserved under edge deletions. Okay, so in fact, any property that is preserved under edge deletions, that forms a downset in this fashion. So that's about planar graphs. Similarly, collection of all bipartite graphs. If you consider one bipartite graph as your set S, which is again identified by the collection of edges, removing 0 or more elements from that set corresponds to removing 0 or more edges from that bipartite graph, and hence it remains bipartite and in the collection. So that's also a downset. In fact, these kind of graph properties are called monotonically decreasing properties. If a graph, these are properties where if a particular graph has it, then all the subsets of that, all the subgraphs of that graph also has it. These are called monotone decreasing properties, but we will call them downsets. Similarly, think about all 5 colorable graphs. Just some non-examples, some sets which are not downsets, all subsets of 10 which contain 5. Okay, you should pause and verify that it is not a downset. Why? Yeah, because for let's say a set which contains 5, you can form a subset of it not containing 5, but that will not be in your collection, and hence this collection is not a downset. Or all graphs which contain a triangle. Okay, this symbol I use for triangle. All graphs which contain a triangle. Why is it not a down close family? Suppose this graph only had one triangle and then you delete that one edge, then you get a graph which does not contain a triangle and hence not in the family. Or all subsets of 10 with size 5, more trivial example, right? Subsets will have size 4, 3, 2, etc. and hence they won't be here, right? But now remember that something not being a downset does not automatically make it an upset. Like, so for example here, 1 and 2 coincidentally turn to be an upset. So, but don't get biased by that. 3 is an example which is neither a downset nor an upset. Okay, so yeah, so in that sense, one property does not, the negation of one property does not imply the other property. What are some easy examples of subsets? Yeah, the first example here, all subsets of 10 containing 5, all graphs which contain a triangle. Remember, once you have a graph with a triangle, adding more edges will not destroy the property that it contains a triangle. Other examples are connectedness, or all Hamiltonian graphs on n vertices. These are properties which are monotonically increasing. Planarity, four-colorability, etc. are properties which are monotonically decreasing. Connectivity, Hamiltonicity, etc. are properties which are monotonically increasing. Okay, so I leave it as an exercise for you to imagine properties which are not, or collection set families which are not upsets. Okay, let's now record few easy observations. The empty collection satisfies the criterion of both a downset as well as an upset. Okay, because the conditions that we are checking is vacuously true, because the condition only tells something when you have an S in the collection. So if there is no S in the collection, either in this definition or in the upsets definition, it's vacuously true. So empty set is both a downset and an upset. Similarly, the entire power set is also both a downset and an upset, but this is not vacuously true. There are sets in this collection, but you can verify very easily that they satisfy the requirements of a downset and an upset. Now, another easy observation to make is that a downset will always contain the empty set, except in one case, which is this case. Okay, except when the collection itself is empty, any downset should contain the empty set. Why? Because even if your collection contains one set, if it's already an empty set, then you are done. But even otherwise, if it contains even at least one set, then empty set is a subset of that set. Okay, so empty set qualifies to be this S prime here, and hence that empty set should be in the collection. Right? Similarly, the universal set is part of any non-empty upset. Again, the only exception is when the whole collection itself has nothing in it. It's an empty collection. Otherwise, the universal set is part of every non-empty set. Okay, so these are very easy observations. We'll make a few more observations later on, but let's also see one concrete example with n is equal to 2, or other words, the universal set is just 1 comma 2. Okay. The universal set, just the two elements, 1 and 2. So what are the potential downsets here? You can verify that these 6 are the potential downsets that you can form from within the power set of U. The empty collection, the collection which only contains the empty set, singleton 1 and the empty set, singleton 2 and the empty set. So singleton 1 and the empty set, just check if it's a downset. You can say that, okay, 1 is in the collection, which means its subset should also be there, but the only subset other than 1 itself is 5, which is there in the collection, and so, right? So these are the downsets that you can form. Similarly, you can pause and verify that these are the upsets that you can form. Okay. So here I wanted you to notice something. I have sorted this U1, U2 to U6 in a particular order. Okay, what is the order? First, maybe if you did not get it, I want you to pause and verify, like, what is on what basis did I decide this choice? Okay, yeah, I'm assuming you would have guessed that U1 is actually the complement of D1, but complement where? Complement under the power set. Okay, so U1 is the power set of U minus D1. Similarly, U2 is the power set of U minus D2, right? D2 contains phi, U2 contains everything but phi, and so on. So this is how I have written, which leads us to another observation, that if D is a downset, then its complement under the power set, okay, the 2 power n denotes the power set of the domain, power set of the universe being set n in this case. So yeah, if D is a downset, then its complement under the power set is an upset. Okay. But there is also another observation. If D is a downset, then if you form another set D prime by complementing each set in your collection. Okay, now the first thing to be clear is, why is the observation 5 first line different from the second line? In the first line, we are not going inside the collection and complementing each set. We are taking the complement of the collection itself under the power set. Whereas in the second line, in constructing D prime, we are going inside each of these set and then taking a complement of that set. Okay. So for example, if D has some k elements, D prime will also have k elements. Whereas in the first line, if D has k elements, this would have 2 power n minus k elements. Okay. So this also I want you to verify that it is an upset. This is because the supersets. Okay. So here also, actually, you can, I can ask this as some kind of, match the following question, where I'll ask what is D1 prime, where the prime denotes this going inside the family and complementing each set. Then D1 prime will be U6, D2 prime will be U5, and so on. So yeah, so there is a, if I had reversed this U1 to U6, then it will match this. Okay, so that's also one way to go from a downset to a upset. Okay, and we may use these two. Many of the properties remain true between two downsets. We'll prove it usually, between two downsets, and then we will get the same property between two upsets. And in order to prove one from the other, we will use these kind of relations. Okay, or I can even, let's get to the main combinatorial theorem that we will see in this lecture. Okay, this is called the Cleatman's theorem. This is from 1966. Though technically there is a theorem called Harris's theorem from 1960, which is very similar. But yeah, but we will, since this is the statement which is cleaner, we will state Cleatman's theorem and give a proof, right? So it talks about two downsets. Okay, so both this A as well as B are both downsets of some universal set n. Okay, and here actually this n will feature out, this n will figure out in the conclusion also. So even though we can define downsets without resorting to a universal set, in this theorem we need that these are downsets of a particular universal set, and without loss of generality we take the universal to be the numbers 1 to n. In fact, you could have taken any set of n elements. Okay, and then what is the conclusion of the theorem? It says that A intersection B. Okay, now this is also one place where you should be very careful. A and B are families of sets. So A intersection B is essentially another family of sets. what does that family contain? It contains all those sets which are in the collection A as well as in the collection B. Okay, so yeah, think about it that way. It's actually, I mean, just straightforward, but I want you to be careful that this is not, we are not going inside the collection and taking a pairwise intersection among the sets in the collection. No, that we will do sometime 2 classes down the line. But today it's a very simple intersection of collections. These are the sets which are common in both the collections. Okay, and we are saying that the number of such common sets is greater than or equal to the product of the cardinalities of each of the collection. Okay, it's greater than or equal to the number of sets in A times the number of sets in B scaled down by 2 power n. Okay, so this is what this is, right? So before proving this, let us see how this can be interpreted as a statement about probabilities and positive dependence. Okay, so let me divide both the sides by 2 power 2n. Okay, or 2 power n times 2 power n. So this left side will get a 2 power n in the denominator, and the right side will get 2 power n times 2 power n in the denominator. But now this gives this helps us giving a probabilistic interpretation for the 3 terms here, right? So what is okay, let's think about this term. Now what is this a divided by 2 power n? So remember, cardinality, this A is a collection of subsets of n, which means it's a subset of the power set of universal set, right? Of the universal set. So this is the number of sets in A divided by the total number of possible sets. Hence, I can think of this as the probability that a subset S of n picked uniformly at random from the power set belongs to A, right? Belongs to the collection A. Right. So remember, this power set 2 power n has 2 power n elements, and if you pick one of those sets uniformly at random, each set gets a probability 1 by 2 power n. Since your collection has cardinality A many sets inside it, the probability that the choice would be something in collection A is this ratio. Okay, that is this ratio. But there is also an alternate interpretation which turns out to be the same. Instead of, there is a way to pick this subset of S uniformly at random in a decomposed fashion. I mean, we are not going to use any of this in this proof, but I'm just stating it upfront that this is also equivalent to this random experiment of picking a subset of a domain uniformly at random is also equivalent to constructing a set in steps by picking each element of the domain independently and uniformly at random. Okay, so here the independence is important. The choice of one element should not influence the decision of whether another element is included or not, and it should be uniform in the sense that each element comes into your set with a probability half. Okay, so that's the uniform part of it. This you can actually verify that this is going to be the same, because even in this model the probability of picking any set is half into half into half n times, so it will be 1 by 2 power n, and hence this probability interpretation works for this experiment as well as this experiment. Probably I am kind of elaborating it unnecessarily. We have seen in multiple cases that these two models are essentially the same. When instead of saying color each vertex independently and uniformly with 3 colors, I could have said pick a 3 coloring of this graph uniformly at random from all possible 3 colorings. Both turn out to be the same experiment. It doesn't look so, but all the probability distributions that both of them produce are the same. In fact, it's also connected to that mutual independence that I was speaking about. Certain events are obviously independent under this decomposed model, but it turns out that they have to be decomposed. They have to be independent even under the model of picking one 3-colored graph uniformly at random. So yeah, it's a point to ponder, but it's not about, let's not digress now, because already this theorem's proof is a bit of a clever proof. So let's not digress now. And yeah, just so now we see that once you have interpreted these 3 things, now what is cardinality of collection B by 2 power n? Probability that a uniformly chosen subset of n is found out is present in the collection B, that is this probability. Similarly, this probability is that of finding your uniformly chosen set in both A and B in the common collection, right? And then I can rewrite this inequality here as something about the probabilities. Okay, so here what do I mean by a probability of A? The random experiment is picking a set uniformly at random. So A is also, a collection of subsets, right? Sorry, it's a collection of sample points, right? Since each sample point is a subset of n, this is a collection of sample points, and so this interpretation makes sense. Here also, I mean, if it's not clear about it, you should first write it as probability that S element of A intersection B is greater than or equal to probability that S is a member of A times probability that S is a member of B. But then, it is almost like writing your outcome is a member of the event. In a probability notation, we generally don't write it so elaborately. We will just write it as probability of the event. Okay. So, in fact, these downsets or any family of sets A and B, if it's a collection of events from if it's a collection of sample points from the same experiment. Okay, now that may be confusing to some, because why do I say collection of sample points? Because here the experiment produces a set, so one set is a sample point. Okay, so these are collections of sample points, and hence these are events. Okay, so some people call this A and B not just as two downsets of n, they will call A and B to be monotonically down events or downward closed events. Most of the time you call them as monotonically down events or monotonically decreasing events. Okay, so think about, make sure that you appreciate the script A and script B, the collections A and collections B as events, in their own rights. And don't forget that the sample space is the power set of the universal set. Okay, with that, so this interpretation we can keep aside. So we will go back to the combinatorial way this is stated, and then prove the theorem in this version. Okay, so remember what we have to, what's the hypothesis? We are given that A and B are downsets, and what we have to prove is this inequality. A intersection B is lower bounded by, cardinality of A intersection B is lower bounded by product of the cardinalities divided by 2 power. Okay, so our proof is going to be by induction on n. And the base case, let's take n equal to 0 because it's easier than taking n equal to 1. But now if the domain is the empty set, okay, n equal to 0 means this set of the first n positive numbers will be the empty set, right? But in that case, what is its power set? Power set of the empty set actually contains one element, okay? It contains the empty set, okay? Power set of the empty set contains the empty set itself. It's a, like also you can verify it by cardinality, 2 power 0 has to be 1. So it contains the empty set, but then what are the possible downsets which I can choose from within this? Actually, I can choose 2 downsets. One is the empty collection, which is always a downset, and here the second choice for a downset happens to be the universal set. I mean, here the power set itself, the phi, right? So these are the only 2 choices that I have for a downset, which means your A and B. It's either that A is D1, B is D2, or both A and B are D1, or both A and B are D2, or A is D2 and B is D1. These are the only choices you have, right? So it's very easy to analyze this case. And what is our target? Our target is to show that cardinality of A intersection B times 2 power 0. The n becomes a 0, which means is a 1. So we have to show that cardinality of A intersection B is greater than or equal to product of the cardinalities. Now, this right hand side has the product of the cardinality. So if either of them is D1, if either collection A is D1 or collection B is D1, this is 0, and this is anyway a non-negative number, so the inequality is satisfied. The only remaining case is when both A and B are D2, which means this is 1, this is also 1, so their product is 1. But fortunately in this case your collection A intersection B is also D2. It is D2 intersection D2, so it's D2. So its cardinality is also 1, and hence this inequality is indeed satisfied. Okay, so that's what we see here. Okay, so this shows you that the base case is done. Okay, now let us go to the induction step. Okay, so let n be more than 0. So your domain has at least 1 point. Okay, in particular, the domain that we are considering is the set 1, 2, up to n, and both your script A as well as this script B are downsets, right? So they are subcollections from the power set of your domain. Now let's first analyze this first downset, the downset A, and we are going to split A into two collections, okay? A n bar and A n, where A n bar are all those sets in the collection which does not contain n, okay? So here, yeah, n bar is those sets in the collection. So we are splitting your collection A, right? Your collection A has sets, right? Some S1, S2, some K sets, right? Now you are splitting this collection into some two groups, okay? One group, you call it A n bar, those sets SIs which do not contain n, and another collection A n, which are those sets which indeed does contain n. And from the sets which do contain n, we remove n from each set in the collection and form a new collection which we call A n prime, okay? So this A n prime is not a subset of A, it's not a subcollection inside A, because you are tampering with each set. From each of these sets we are removing n. In fact, we can do that because we are only doing it within A n. Those are the sets which contain n, okay? We will see how it is used later, but these are the three sets that we will consider: A n bar, A n, and A n prime. Now what are some easy claims? This A n versus A n prime is a partitioning of A, right? Which means every set in this collection either belongs to A n or it belongs to A n prime, but not both, okay? So this is a partition, which means it's a disjoint union, right? So that this property we will, it's easy to see, but we will make use of it, okay? Verify that also. And A n, the second property that I want to draw your attention to is that A is a downset will imply that A n bar is also a downset, okay? So think about it. A n bar is all those sets inside A which do not contain n. Now take any, let S be a member of this collection A n, and let S prime be a subset of S. Does it imply that S prime is also in A n? This is a requirement for a downset. Now S prime is already in A. Why? Because S is in A being a downset, S prime is already in A. But if S prime is in A, then since S does not contain n, even S prime does not contain n, and hence that S prime would also have been while doing this partition, that would also have landed inside A n. Okay, so this is a downset. But A n is not a downset. Okay, why? Because A n contains, for example, the set 3 comma n. Okay, this may be in your A, right? But now when you consider one of its subsets, which is 3, and this is in A as well as this is in A n. Okay, this is in A because A is a downset, but this does not fall. When you do the partition, it does not go into A n, it goes into A n bar. Okay, so this S A n does not have the downward closed property. For a given set inside of A n, only those subsets of which also contain n will be there. So, but there are other subsets which do not contain n, and hence it's not there. Or in particular, you can even just verify that A n does not contain the empty set. Okay, so this is clearly not a downset. In fact, that is why we massaged, or we went into inside the collection and did some small tweaking with each set in the collection, so that this A n prime turns out to be a downset. Okay, so think about that. If S is in A n prime, right, that actually means, and let us say S prime is a subset of S, then S is an element of A n prime means S union n is a member of A n, which is anyway a subset of A. So A is a downclosed set. So any subset of this, in particular S prime union n, is also a member of A, because A is downward closed. But this would actually mean that this S prime union n, during this partitioning, because it has n inside, it will go to A n, and once you do this massaging or tampering inside, what you will get is this S prime will be in your A n bar. Okay, so now you read these together. S is in A n prime, S prime subset of S will imply that S prime is also in A n prime. So that tells you that A n prime is also a W, is also a down set. Okay, recall that A n is not. This is the reason why we went for it. Okay, but now this relation tells you that the cardinality of A is nothing but the sum of these cardinalities. Okay, that you should remember. But we can also compare the cardinalities of A n and A n bar. Okay, which is going to be larger. Okay, between this, when you do this partitioning into two, which is going to be a larger set. This is slightly more clever observation. The other observations, if you are familiar with working with downsets and all, that would be immediate. But this is something interesting. We are saying that for any, you pick any set in A(n), okay? You pick any set S in A(n), it has a corresponding set in A(n) bar, okay? Because your S minus this n will surely be in A(n) bar. Why? Because if S is in A(n), then A(n) is a subcollection of a down set A. Hence, all subsets of S are also in A. In particular, S bar S minus n is also in A, right? So we'll first get that S minus n is in A. And hence, during this partition, since S minus n does not contain n, it will go to A(n) bar. Okay. So I am saying, like, you can kind of do a one-to-one matching for any set in A(n) bar, right? I have a partner in A(n). Sorry. If for any set in A(n), I have a partner in A(n) bar, and A(n) bar have more sets. A(n) bar can have actually some sets on which if you add an n, that is not necessarily in A. Right, there is no upward closure here, right? We are only talking about down sets. So in fact, your A(n) can even be empty. If your entire collection does not contain n, then your A would be completely equal to A(n) bar, and your A(n) can be empty. So this is not an equality, but what we are saying is that A(n) bar is at least as large as A(n), because for every set in A(n), I have a partner in A(n) bar which I obtain by removing. So this is in some sense gives an injection from A(n) into A(n) bar, and hence you can prove that you get an injective function from A(n) to A(n) bar by taking any set to that minus this, and since this is an injection, the codomain has to be larger. Okay, so A(n) bar cardinality is larger than or equal to A(n)'s cardinality. But now A(n) and A(n) prime have the same cardinality. There is no collapse happening there, because from every set we are removing n, and there was n originally. Okay, so there is no collision happening here. So A(n) and A(n) prime have the same cardinality. Okay, so this property also we will make use of. Now the same thing we will do with B, right? So what would be Bn prime? Bn prime would be all those sets in B such that n is not an element of S. Okay, so remember, when it is n prime, it's about not an element. Okay, similarly, Bn will be all those members in B such that n is in that, right? And Bn prime is obtained by removing n for each set in Bn. Okay, so here the key thing to remember is that it's only about Bn, and I can write the similar claims, right? Your B will be partitioned into Bn bar and Bn. The second observation would be the easy one, that Bn bar is a down set. Next would be that Bn prime. Bn is not a down set, Bn prime is a down set. And about cardinalities, again your Bn bar is going to dominate Bn, which is actually equal to Bn prime. Okay. So with this claims, we are ready to show what we want, that A intersection B times 2 power n is lower bounded by cardinality of A times cardinality of B. Remember, we are doing a proof by induction, so we are assuming this claim for n minus 1, when the domain only has n minus 1. Okay, so let us start with, in fact, I'll end up, I think, showing it this way. So let's start with the left hand side. Okay, so what is A intersection B? Remember, A was split as AN union AN bar, and B was split as BN union BN bar. So I can this is going to be a very long lecture. Okay, but anyway, let's finish this off maybe by taking 10 more minutes. So now I claim that all the members in this intersection of the collection are of this form. Okay, so technically if you expand A, if you write A as a partition of two sets and B as a partition of two sets, you will actually get 4 terms, but 2 of those terms are empty, right? AN intersection BN bar is empty because AN contains only those sets which contain N, BN bar contains sets which do not contain N, so there is no common set in the 2 collections. That is why the 2 cross terms disappear and you are only left with AN intersection BN as well as AN bar intersection BN bar, and it is easy to see that this is also a disjoint union. Why? Because this collection contains, all the sets in this collection contain N, none of the sets in this collection contain N. So this is a disjoint thing. So since it's a disjoint union, the cardinality just sums up. Right? So yeah. Now this line, the only thing I have changed is I have put in the hashes here. Okay, so that now I can use the induction hypothesis. Right. By the way, this is I'm not saying AN intersection BN is equal to AN prime intersection BN prime. No, I'm only saying that the cardinalities match. Okay, so think about that. This cardinality of AN is equal to cardinality of AN prime. That similarly for BN, that we know. But even in the intersection, that is true. Okay, so now this is talking about the cardinality of intersection of 2 down sets. This is also talking about the cardinality of intersection of 2 down sets. But now both of them, though you have this subscript n and all here, all of them are actually from the domain which is, right, because these are all subsets of the power set of 2 to the power n minus 1. Right, because A n bar and B n bar do not contain n, so I can as well treat them as subsets of P, the power set of n minus 1. And here the reason to go to the primed version is also that now I can treat them as subsets of 2 to the power n minus 1. Okay, because none of them contain n. I have intentionally or forcefully chucked out n from these collections to go to the primed versions. Hence the induction hypothesis will apply. And I can lower bound this cardinality of this intersection with, remember it's 1 by 2 power n minus 1. Okay, don't forget this n minus 1 here because it's induction hypothesis times the product of the cardinalities. Same thing here, 1 by 2 power n minus 1 times product of these cardinalities. Okay, next is in my opinion, the cleverest part of this proof. Okay, first I will tell it in terms of formulae, and then I will tell it in terms of a picture. Okay. So, I am calling this A to be I am calling little a to be the cardinality of A and little b to the cardinality of the collection B, number of sets in the collection B. And epsilon 1 and epsilon 2 are 2 non-negative numbers, okay, greater than or equal to 0. Now, I know that and I am going to write this A n prime's cardinality and A n bar's cardinality as A by 2 minus epsilon 1 and A by 2 plus epsilon 1. So, if you add up these two cardinalities, of this and this, then you know that you get the cardinality of A, right? Because this relation is there, and in terms of cardinality, this guy's cardinality is equal to the cardinality of the primed version, right? So, maybe I can note it here as some property. Cardinality of A is equal to cardinality of A n prime plus cardinality of A n bar. Cardinality of A n follows because it's a partition, and A n and A n prime have the same cardinality. Simple observation, right? And this is what I will denote by A. And I am going to, because of this observation, I know that A n bar, this guy is the larger guy. So this is some A by 2 plus epsilon 1, and this is some A by 2 minus epsilon 1, so that they add up to A. Right? So I can be sure that epsilon 1 is non-negative because A n prime is the larger one. That was a nice observation that we had made. Similarly, we will do it for Bn also. this observation 5 would be cardinality of B is equal to cardinality of Bn bar plus cardinality of Bn prime, which if I call them as B, this will be B by 2 plus some epsilon 2. It may not be the same epsilon 1, right? B by 2 minus epsilon 2. Again, because Bn bar is the larger of the two. That's all that I have done here, okay? This cardinality, you can rewind back and verify. This is the minus epsilon 1. This is the plus epsilon 1. This is the minus epsilon 2, this is the plus epsilon 2. In fact, here the critical observation is that the smaller guys get multiplied together and the larger guys get multiplied together, okay. Now you try to expand this out and yeah, maybe you should pause and try to do it, right. You will see that this AB by 4 comes plus here as well as here. This plus epsilon 1, epsilon 2, that also occurs positively in this part and in this part. The other two terms actually cancels out, okay, and then this is what you will finally get, okay. This another, I'm not taking out a 2. In fact, this has become 2 power n, which means I'm dividing. Yeah, I'm multiplying, I'm in fact pushing a 2 inside so that this becomes AB plus something. Now remember, these two guys are non-negative, so this is non-negative. So I can lower bound it by 1 by 2 power n AB, right? And remember what was AB? This is nothing but 1 by 2 power n cardinality of A, cardinality of B. And this is our right hand side, okay? This was our, where were we? Yeah, this was our right hand side. A cardinality of A times cardinality of B divided by 2 power n. Okay. Now, yeah, but now what is a, I mean, this looks like kind of a clever calculation. I mean, I do not know who came up with, I mean, how it was originally proved. I had to kind of, struggle a bit to prove this, because Allen and Spencer does not prove Kleitman's theorem directly. It proves a very, very strong generalization of it called the four functions theorem, and then derives Kleitman's theorem from the four functions theorem. But I thought it is still instructive to see its proof standalone, because that itself has some nice tricks to it, okay. But this last step about this inequality, I think that's a clever step, and you should also try to imagine that visually. Think of a rectangle with one side as A and the other side as B. I'm not, though in the picture it looks like A is more than B, that's without loss of generality, not needed, okay. Now then you kind of put one horizontal line at some place which is B by 2 plus some non-negative quantity, and a vertical line at half point plus some epsilon 1 quantity. Then what this is saying is that this shaded area plus this shaded area, right, that would be at least half of the total area. That's what this inequality is saying. Or equivalently, I can say that the shaded area dominates the unshaded area, okay. And I want you to think about a picture proof, think of this as a paper sheet, and maybe you can cut and fold or something, and then try to give a picture proof of this relation. Then you won't have to do any of the simplification, just because this guy dominates this guy dominates this guy, and this plus this adds up to A, this plus this adds up to B. From this picture, you can make this final conclusion here that it is half the total area. So it will be half of AB, this 2 power n minus 1, and that halves 2 will give you the 2 power n. But that's for a thought exercise for it, okay. So yeah, we will stop for now. I thought we will be able to, we'll be doing some application of Kleitman's theorem also, but maybe in the next lecture we will do that, okay. Thank you.